section 11.3. The actual title for this section is the number E. But I'm going back to 11.2 for a second because I wanted to talk about this general formula for exponential growth and decay. N equals N naught of 1 plus R to the T. Okay? N is your final amount, N naught is your initial amount, R is your rate of growth or decay per time period, and T is the number of time periods. Okay? This general formula is where the compound interest formula comes from. R being the rate of growth or decay per time period. That's why they take R divided by the number of times compounded per year, because that's the number that would be per time period. Okay. We're going to use this to calculate something to do with population. So here's the first problem. Okay, the average growth rate of a city, or of the population of a city, is 7.5% each year. The population is now 22,750. Write the function to model this situation. Okay, then use it to find blah, blah, blah. First, start with writing the function to model the situation. Okay, so using N equals N naught 1 plus RT. We're going to use that. We're going to plug in the information that we know. Okay. T is going to be our function because this is a function over time. So T is going to stay T until we want to use it. N is going to stay N until we use it. So this is going to be N equals our first amount, our initial amount, which is 22,750 times 1 plus 0.075, and you must always do, when they give you a rate as a percent, always convert it to the decimal, to the t power. So our function that's going to model the situation is 22,750 times 1.075 to the t power. There is our exponential model. Now we're going to use it by simply plugging in 10 for t. So to project for 10 years from now, 22,750 times 1.075 to the 10th power. And you may use your trusty calculator for that. The projected population would be 46,888. Okay. Now let's talk about E. The number E is defined by, as n approaches infinity, 1 plus 1 over n to the nth power is going to approach E. E is a special number. It is specific. It's non-repeating, non-terminating. It's another irrational. It's 2.7182812828, and it will continue on in that fashion. Euler is the one that came up with it. That's why it's called E. It's considered Euler's number. Just some interesting facts. With exponential growth and decay, same thing. N equals N naught E to the KT. N is your final amount, N naught is your initial amount. E, of course, is E, which represents this number. We have a button on the calculator for that. K is a constant, and T is time. Okay? Depending on your situation, you might use it somewhat in physics. There are some applications with the number E in physics, and the most popular one that I know of has to do with the financial world. If anything is ever compounded continuously, that is E. That is where E comes into play. So, using that formula, here is an exponential growth dealing with financial investments. Okay? A equals PE to the RT power. When I taught the financial class, they're like A equals PERT. That was one way to remember it, but you have to remember that E is that special number. Okay? A is your ending amount, P is the principal, which is the amount you invest, R is the interest rate, and T is the time in years. Okay? We're going to compare the ending balance of a 30-year investment of $15,000 earning 12% interest compounded continuously. This phrase right here, compounded continuously, is the one that tells you to use this one. And we're going to compare it to the same type of investment, compounded quarterly. Well, compounded quarterly uses the other compound interest formula. Okay, so with that, I have my next page, or my next little slide set up. We're going to have two formulas. We're going to have A equals 15,000 times E to the RT power, where R is your interest rate, always as a decimal, and T is your number of years. It is a 30-year investment. And by the way, the longer you invest money, the longer it sits there, the more money you make on it. Okay, so that 15,000 sitting for 30 years is going to increase to $548,973.52. Okay, it seems like a really long time, but look at how much money you'd have after 30 years. So if you had $15,000 in the beginning, like say when you're 20, and you can just put that into an account and leave it sitting there, then that would be a very good thing to do, because that would be one heck of a nest egg for a retirement fund. But let's compare it compounded quarterly. What's going to happen if it's not compounded continuously? How much is it if it's only compounded quarterly? Okay, 15,000 times 1 plus your interest rate as a decimal. Quarterly is 4 times a year. And then this is going to be the 4 times 30 power. Okay, so 15,000 times 1 plus 0.12 divided by 4 raised to the power of 120, because 4 times 30 is 120. In this case, my ending amount is $520,664.81. Okay, so you can tell obviously that one is considerably less than the other. The difference, the actual difference is $28,308.71. Okay, so compounded continuously versus compounded quarterly. If it were compounded monthly, it would be less. If it were compounded daily, this amount would be more, so therefore the difference would be less. Okay, the more often it is compounded, the better the investment.